Hi everyone, this is the E3 lecture on metal cladding. So we're going to be looking at both roof and wall systems today. But I wanted to start with this image, which is a section axonometric, and just to say to you that this is a very efficient drawing. It shows the structure of the building. It shows the suspended ceilings. It shows the envelope system. It shows that the top story of the building sets back and that it has a different kind of structure on the top floor, which is a steel framed structure, and that there is a planted roof. So I'd like to encourage you to do these kinds of drawings or a drawing like this for your project in Studio. Okay, so historically, metal has been used for centuries for roofing for important buildings. And so the Pantheon has a lead-coated copper roof, and cathedrals and town halls and libraries, important civic buildings typically had either lead or copper roofs. So the image on the left is an aerial view of Oxford University, and you see both lead roofs, that is the grey metal roofs, and the bright green copper roof of the Bodleian Library. Uh, Also, during the past 150 years or so, metal has been used as a substitute for stone. So we talked about this right at the beginning of the semester when we talked about cast iron facades, which you see on the right. In this case, molten iron would have been poured into molds to make manufactured, mass-produced cladding. So the molds were reusable, could be used over and over again. And this is a non-structural skin. A contemporary example of a cast facade was the Museum of American Folk Art by Todd Williams and Billy Chen. And these are cast bronze panels uh, which have a very rugged and pitted surface intentionally. Metal sheet has also been used as a substitute for stone. And so what you see here is a dormer window surround that looks like it is traditional stonework for a building, but it's actually made of galvanized steel sheet that is cut and soldered. And so the cornice of Hayes Hall also looks like a traditional stone cornice, and it is made of sheet metal, as is the metal cornice of Parkside Candies. So today, many different metals are used. Historically, we still use copper cladding and lead for both walls and roofs. And in fact, when the Cathedral of Notre Dame burned last year, its lead roof became a very controversial subject because when the lead roofing burned, it released particles of lead into the air, which are obviously dangerous for health and safety. Lead is typically just fine. It's just when it is lead dust or lead particles that it becomes dangerous. And lead and copper are prized for their very long life. So, but in addition to these traditional metals, we have a number of different metals that we use for cladding systems. Steel and aluminum cladding systems are the most common and very widely used. Corten steel, which is self-rusting steel or also called weathering steel, uh, is also widely used these days. So this is steel that is fairly thick, say eighth of an inch thick. It rusts, and the rust then forms a protective layer that prevents any further corrosion. And the color of Corten is this very, very intense orange. Uh, on the left is an early building by Morphosis, and this is galvanized steel sheet. So the galvanizing is zinc. If you recall, it's when these panels are dipped in a bath of molten zinc. So here we have zinc and steel then to make these panels. And the assembly system here is the same assembly system for the paint booths in Crosby Hall. We looked in the previous lecture at the art school in Toledo by Frank Gehry, and this is lead-coated copper. So this is used instead of just copper because it's much lighter in weight. Lead is super, super heavy. So if we can just put a very thin coating of lead on copper, we can have the appearance of lead without the weight. And the lead coating prolongs the life of the copper. It gives it a longer life cycle. So these are just a few examples of the kinds of metals that are being used today. The most common metals that are used for cladding are steel and aluminum. And if we were to compare them, there are many different attributes that we can compare. In terms of weight, steel is heavier and therefore may require more supporting structure. And aluminum, as we know, is super, super lightweight. So this is why aluminum is used to build airplanes and boats. In terms of impact damage, steel is very tough. It's highly resistant to impact damage. It doesn't dent easily. And aluminum, as we know, uh, is prone to dent very readily. So it dents easily. It can easily be damaged both during construction and during the life of the building. In terms of cost, steel is less expensive, aluminum is more expensive. There's another attribute that becomes quite important, which is corrosion. As we know, steel corrodes, it rusts away, and it can't be used in its raw state except for when we're using Corten cladding. So steel requires protection. Aluminum has no requirement for protection. Nothing is needed. It oxidizes, and the oxidation is self-protecting. The only drawback is that when aluminum oxidizes, it's a kind of dull gray color that looks rather dirty, so isn't terribly desirable as a building finish. There's also a factor called bimetallic corrosion, and this is what happens when two different metals come together. So in this regard, steel is not temperamental. Steel is very compatible with most other building materials. Aluminum, on the other hand, is extremely temperamental. It doesn't like most other materials, and so it has to be isolated from other metals like steel, copper, or lead. It has to be isolated from preservative treated wood. It has to be isolated from concrete. And this isolation is usually a coat of um, tar-based paint, or it could be a thin layer of neoprene, which is rubber. In terms of sustainability, um, if we think about embodied energy, we know from the sustainability table that if wood is the factor of 1 in terms of embodied energy, that steel requires 24 times as much energy to make the same volume as wood. And aluminum requires 126 times as much energy as the same volume in wood. If we think about raw materials, both are made from very plentiful raw materials. Steel is made from iron and carbon, which is readily available, and aluminum is made from bauxite, again, a very plentiful raw material. The manufacture of both metals produces high levels of pollution, and both metals are uh, are heavily recycled. They are able to be recycled. They are readily recycled. So the metals have some drawbacks and they have some benefits. If we think about the color of metal cladding, and this is all metals now, not just steel and aluminum, there are two general strategies, which we see in this image of the Experience Music project by Frank Gehry. One is to use a metal for its inherent natural color. So the silver volume that you see in this image is stainless steel. That is the metal itself. The second strategy is to apply colored finishes to metals. So the blue volume that you see is an enamel-coated steel, and the iridescent volumes are steel that has been dipped in an acid interference bath. The interference interferes with certain wavelengths of light and allows other wavelengths of light to come through, and that's what gives the metal its iridescent quality. When we think about choosing the color for metal cladding, we might have multiple considerations or criteria. One would be aesthetics. What do we want it to look like? Two is cost. How expensive is it? And three, issues related to sustainability. So if we choose dark colored metals, or we make metals dark coated through the coatings that we apply, those will absorb the heat and light of the sun and increase the running costs of the building. If we choose light and reflective colors, these will reduce the amount of heat absorbed by the metal cladding and will reduce the heating and cooling costs of the building. Regarding fire resistance, no metal cladding system has any fire resistance. So this is different from, say, concrete cladding or brick cladding. If we're using concrete or brick, it enhances the fire protection of the external envelope. If an external envelope with metal cladding needs to be fire rated, that has to be achieved in the backup layer because the metal doesn't contribute at all in this regard. So, with this general introduction, then, I'd like to talk about standard metal cladding systems and assemblies. Broadly speaking, there are four types of metal cladding assemblies. Uh, and I'll just go through the list now, and then we'll talk about each one in a little bit more detail and look at some examples of each. The first system is flat sheet. The second system is corrugated sheet. The third system is composite panels. And the fourth system is rain screen. So historically, the trend has been to reduce the amount of metal used to make the building envelope. And this, of course, is to use, the reason for this is we want to use less metal in order to reduce the cost. Reducing the cost not only of the cladding itself, but of all of the supporting structure behind. The less weight we have, the less structure required. And so to do this, ways have been developed of using thinner and thinner sheets of metal. So this kind of economic imperative, which is now also driven by an environmental imperative to use fewer natural resources. And so this image, if we think about the cast iron cladding system from the 1890s, this would be somewhere between 1/4 and 1/2 inch thick. The lead-coated copper panels or cladding of the Toledo Art School is very thin sheet metal. So let's look at each of these assemblies, and we'll start with flat sheet metal with the Toledo Art School. And for each assembly system, we can talk about how the assembly system works, what might be a typical range of span, and the typical jointing system. So this is flat sheet metal. It's very thin metal and it has 0 spanning capacity. It requires a continuously supporting underlayer. So in this particular case, the plywood sheathing is supporting the metal cladding. The joints with a flat sheet metal system would typically be interlocking joints. So we talked in the previous lecture on roofs about seamed metal roofing systems and the seamed metal roofing and wall system of this building, in which we saw that 2 pans of metal are brought together with a cleat in the middle, and then those elements are folded over several times. So the folding produces the interlocking joint. The second assembly system is corrugated metal sheet. And the corrugations are very typically ranging from 2 to 3 inches deep, and these can span from 4 to 8 feet. Now, there are, of course, hundreds of different profiles of corrugated cladding, and you can get very deep corrugation. So if you wanted to go up to, say, a 7-inch deep corrugation, you could span up to 16 feet or around 16 feet. The jointing in this system is overlapping, both on the end joints and on the side joints. So we simply slip one piece over another to overlap the corrugations in either direction, and that is what seals the joint. So this is an architect's house in London, and you can see that it is corrugated steel sheet. There are actually 2 layers of corrugated steel sheet. one on the outer face of the building and one providing the interior finishes. And in between them is loose laid insulation. So the insulation is not bonded to the corrugated metal, it's simply loose laid. And you can see that this architect has made the corner condition, has covered the corrugations with a steel angle so that we don't see into the corrugation. So this is a very kind of crisply detailed house. The third type of metal cladding system is composite metal panels, and these can span up to 12 feet. In this system, very thin sheet metal is bonded to another material to give it spanning capacity. And so that other material is typically rigid foam insulation. And so in this case, the insulation becomes structural. It's not holding up the building, it's giving the cladding panel enough stiffness to span. So cladding panels range from, say, 2 to 6 inches in thickness generally, and they were developed in the 1970s in response to the energy crisis when insulation and thermal performance of buildings first became a real concern. Because the panels are thick now, the joints are typically made with another material. And so there are a number of different metal pressure plates or what we call top hat sections that can make the joints between the cladding panels. And another common method is a neoprene gasket. Neoprene is a black rubber material. This would be similar to the gaskets that hold the glazing on your automobile. And so an early example of a composite metal panel building is this youth center outside Paris by the French architect Jean Prouvé, which was completed in 1966. And I like to show this project because the section on the bottom left is if you drew that section for your studio professor, your studio faculty would probably say, that's an impossible section. You can't have a section that thin. You need some structure here. But in fact, the skin of the building here is also the structure, and there is no other supporting framework, only the composite panels. And so this then is a shell structure in which the entire surface is working structurally. The skin and the structure here are monolithic. They are one thing. So these composite panels are three materials bonded together. The innermost layer is plywood, a thin layer of plywood, and then there's a thick layer of rigid insulation, and on the outside then a very thin layer of aluminum. And the jointing system is, so here you see the section of the panel at the bottom with the wood on the inside, the thick layer of rigid insulation, and a very thin layer of wood on the outside. The jointing system is a recess that is built into all of the panels in which you can insert bolts and bolt the panels together. And then the joints are sealed for weather protection with a neoprene gasket inside and out. So that's what gives the black line both inside and out. So when we talked about the Sainsbury Centre in an earlier lecture, we were talking principally about the steel structure of the building. So this is the building that was completed by Foster and Associates in 1978. And you remember that the structure is comprised of triangular steel columns that are made of circular section hollow steel tubes and triangular steel roof beams that are also made of circular section steel tubes. We didn't talk about the cladding in detail, but we will do that now. So you can see that the cladding wraps the outside of the structure. And these are composite metal panels. So and at the time, this system was very innovative. It was quite radical. So you can see in the axonometric drawing that the same system is used for the roof and the walls. The entire building is clad with just 5 different panel types. And so the panels are completely interchangeable and movable. They are highly standardized, so the dimensions are coordinated and they are modular and repetitive. There are just 5 panel types for the whole building. So there are 3 kinds of flat panels, which are these profiled aluminum panels, louvered panels, and glazed panels, and then 2 different curved panels to make the joint between the wall and the roof. And so the curved panels are either profiled aluminum or glass. And these 5 panel types do the whole building. The panels are super lightweight, and so they are 6 feet by 4 feet by 3 inches thick, and the very thin aluminum is bonded to both the top face of the insulation, which is outside the building, and the interior face of the insulation. So this cladding system provides both an interior and an exterior finish. And it was the fact that they are super lightweight means that they can be handled by 1 or 2 people and can be moved around. So if they want to move the skylights, they could do so. So the materials here then are aluminum and rigid insulation. And you can see that the surface of the aluminum panels is profiled. It's a ribbed surface, and this is true both inside and out. This is done in a vacuum press with very thin aluminum, which is called superplastic aluminum. So that doesn't mean that it has plastic in it. It means it has a bit of copper in it so that it becomes much more malleable and can be easily vacuum formed. The silver that you see, the building is silver, the finish is silver, and this is a painted finish applied to the aluminum. It's not the aluminum itself. So it's a factory applied paint finish, very high specification. Uh, and this is because, as I mentioned before, when aluminum oxidizes, it's a dirty gray color that is not very appealing. The ribbing of the panels helps to increase their stiffness so that they can span, and it also means that the panels do not streak when it rains. The bottom image here then is a detail of the cladding panels and how the joint system works. So the circle in this drawing is one of the legs of the triangular steel columns, and then there is a steel subframe or secondary framing which carries the cladding panels. So in the axo at the top of image, you see the primary steel structure at the rear of the drawing, and then you see the verticals and horizontals of the secondary structure that is going to carry the cladding panels. And then you see the cladding panels themselves. So in this drawing at the bottom, the panel on the left is one of the solid aluminum panels with very thin aluminum bonded to rigid insulation inside and out, and the panel on the right is one of the glazed panels. And the joint between them is made by the curved black line, which is a neoprene gasket. And this was a very radical innovation at the time. This had never been done before. And this jointing system is very interesting because it does three different jobs at once. It seals the joints between the panels. It works as a movement joint. So the reason that the rubber gasket is curved rather than straight is to allow the building to expand and contract. So this is a movement joint. And the third role that it plays is that each of these joints is a miniature gutter. So this is the rainwater system for the building. There are no conventional gutters and no downpipes and no internal roof drains. So all the water comes off the building in these miniature gutters that occur along the whole length of the building. So the image on the left shows how the neoprene gaskets look when they come to site. So neoprene is joined together by welding, that is, by heating it up until it melts together. So the neoprene was welded or assembled into ladders of neoprene, which were then delivered to site and laid out over the structure. And then the prefabricated metal panels are inserted in this neoprene framework. So here you see a couple of the aluminum panels close up. You see the ribbed surface. You see the black neoprene gasket that seals the joint. And then the grating at ground level. So the water comes off the building and all of the vertical joints, and it drops into a trough in the ground below this grate and is carried away. So again, there are no rainwater pipes or conventional gutters in this building. The roof trusses are not flat, as I mentioned before. They are cambered across the 110-foot span of the building. So they are 6 inches higher at the middle than at the outer edge. And so the roof is very, very slightly sloped. And this, of course, helps to get the rainwater off this basically flat roof, this low slope roof. So the cladding concept here is not simply driven by aesthetic considerations, although those were very important. Um, the, the cladding performs a number of practical roles for the building. It has a number of benefits. So it results in savings of HVAC running costs. Because the panels are highly insulated, they increase the thermal performance of the building, and the silver color is highly reflective, so it reflects the heat and light of the sun and helps to keep the building cool. So no air conditioning is needed. So this building is mechanically ventilated, but it doesn't have a cooling system. It results in savings on the drainage system. So as I said, no conventional gutters or rainwater pipes. Uh, this jointing system is a very good example of integrated design. However, there is an unhappy ending to the story. So when an architect innovates and takes risks, as this architect did with both the cladding system and the jointing system, sometimes problems arise. So on this building, the most radical innovation at the time was the neoprene gasket, and that in fact performed very well, but the composite cladding panels did not. So about 10 years after the building was completed, during a routine maintenance check, the inspector who was up on the roof noticed that the roof panels were sagging, and upon closer examination, he discovered that they were all saturated with water like sponges. So, why did this happen? What was the cause? Well, as I mentioned, aluminum is very antisocial as a material. It doesn't like other materials. And as it turns out, it doesn't like rigid foam insulation. And so there was an adverse chemical reaction between the rigid insulation and the aluminum, and the result is that the insulation corroded the aluminum. So the result was that the entire envelope of this building had to be replaced. Fortunately, because the panels were designed to be um, movable and easy to move around, the building cladding was completely replaced while the building remained open and in operation. So it was obviously done in phases, but the old cladding panels could be popped out and the new ones popped in very quickly. I don't know who paid for this, whether the architect or the client or the cladding fabricator or all of the above splitting the cost. But I do know that the architect supervised the cladding replacement and very much was involved in uh, putting it right, in solving the problem for the client. But you can see that the new cladding panels that were installed are quite different. They are white and smooth, flat white panels. And of course, the white color reflects the sunlight and heat again, but the flat surface, instead of the profiled silver surface, completely changes the appearance of the building. So then if we look at rain screen systems, the fourth assembly system that I mentioned, this we know already is an open jointed cladding system. And so the building that we're seeing here is the signal box Auf dem Wolf in Zurich by Herzog and de Meuron. It was one of their very early projects. And so this is a rain screen system. And the backup wall here is just a very traditional solid wall with a stucco finish. And then there's about a 2 foot wide airspace or cavity. And then the outer skin is this banded copper cladding that you see here. So what you see on the right is a mock-up that they built to test this system. This is not a standard manufactured system. It's a system that they designed especially for this building. So this building houses the signaling equipment for this region of the Swiss railways. And so it's full of equipment. And where it's full of equipment, the cladding is in the closed position. That is, the copper bands are very tightly overlapped and closed. And a few places in the building where people work in the building and need views out, the copper bands twist then to open up and allow views out. So the twisted bands are fixed, they are not operable. So this is the permanent twist. It's not something that is controlled by the occupants. So this is not a machine-produced cladding system, and it uses and it's not using new materials or new assembly systems. It uses a very traditional material, that is copper, to develop an innovative assembly system, an almost handcrafted building envelope. And so if we compare the two, the Sainsbury on the left and the signal box on the right, they're both custom-made metal cladding systems. The Sainsbury Centre is factory-made. All of these panels are machine-made, very precise, mass-produced, using innovative materials and an innovative assembly system, an innovative jointing system. The signal box is a handcrafted system in which a traditional material is assembled in an innovative way. This is the De Young Museum in San Francisco by Herzog and de Meuron, completed in 2005. And you can see that this is also a copper cladding system. And this is a custom designed system by the architects, and it is a rain screen system. So it either occurs as an open jointed outer layer with a solid waterproof backup wall, or in this case you can see it's a perforated outer layer with glazing behind. So where there's a solid wall behind, it's a rain screen system, and where there's glazing behind, it's a shading system. And the strategy here is that there are circles of 5 different diameters punched out of the copper, and that the copper is also dimpled, both dimpled in and dimpled out. These two systems are both set out on their own grids, and the grids do not coincide, and they are superimposed over each other. And so the overall cladding system then looks something like this. All the panels for this large museum are exactly the same size. Every panel has a unique pattern of holes and dimples. The pattern is derived from a photograph of trees in the woods, which was pixelated to get this very abstract pattern. And this image was chosen because this building sits in the middle of a park in San Francisco. This is the Caixa Forum in Madrid, also by Herzog and de Meuron, and this is a Corten rain screen system. So this is open jointed, and you can see some of the panels are solid Corten, and some are perforated with a custom designed perforation pattern that has been laser cut in the steel panels. This too is a rain screen system. And this is the Wiley Theater in Dallas by OMA and Joshua Prince Ramos. So here you can see that the outer skin is comprised of vertical aluminum tubes of different diameters, randomly ordered. And so we get this undulating skin of the building, and then it's open jointed, and there is a solid backup layer behind. The way that they make openings here then is rather clever. So rather than cutting an opening in the tubes, they simply flatten the tubes so that you can see through the assembly. So these are all custom designed systems. These are rain screen cladding systems. It gives you a sense of the range of aesthetic possibilities. If we look at flat sheet metal cladding, we might find cladding like this, which is at the other end of the market. So this is the least expensive metal cladding system, in which we take a sheet of galvanized steel. It is imprinted with a wood grain pattern and then coated with vinyl. And the coating takes place in a factory. It's a factory applied finish, and all of the bending and shaping is factory made. And this is designed as a substitute for clapboard wood cladding for buildings. It has uh, it has a much longer life in terms of requiring much less maintenance. And so you see a lot of it around Buffalo on wooden houses, overcladding on wood houses to reduce the maintenance costs of the wood cladding. So this is thin sheet metal. It requires a continuous supporting backup layer. It can't span, and so it's supported by and fixed to the plywood sheathing of the house. Typically, it's used on houses. And the jointing here is interlocking. At the high end of the flat metal sheeting market, we have the Toledo Art School, which we have already talked about. So this is a flat seamed metal roofing system, also used on the walls. And you can see it has a very crisp appearance. And this is lead coated copper. So here we have Frank Gehry, who is very inventive in terms of the formal character of his buildings, very radical, avant-garde, and yet the cladding system he's using here, the flat seam system, is exactly the same system as the Pantheon. Gehry's building in Bilbao for the Guggenheim Museum also uses a flat seam metal cladding system. And the innovation here is that Gehry caused a sensation by using titanium cladding. So this was the first building of any significance that used titanium cladding. Titanium typically isn't used because it's much more expensive than stainless steel, but there was a blip in the market at the time, and it became less expensive than stainless steel, and so he used it. Here, the titanium is extremely thin, much thinner than aluminum foil, for example, and it requires a continuous supporting backup layer. In this particular case, the backup layer is galvanized steel sheet, not plywood. And so because the galvanized steel sheet can take up the curves of the form. So the assembly here is a backup layer of galvanized steel sheet applied to galvanized steel studs. And this backup layer is absolutely smooth and taut. Then a black layer that you see below is building paper that is applied to the galvanized steel sheet. And then the titanium panels are pre-cut in the factory and delivered to site, and they are installed by hand on the site by workers working from a gantry. So all of these flat seams are handmade by human beings on the building site, exactly the same way as the roof of the Pantheon was made 2,000 years ago. So while the backup layer of galvanized sheet is extremely smooth, you can see that the titanium panels are pillowed, slightly pillowed. And this is intentional. This is done by the human beings installing the panels. It's not poor craftsmanship. It is intentional to soften the appearance of the building and in terms of the way it interacts with light and to give the building a human imprint. So what you can see here is that even though the forms of the building are curvilinear and non-repeating, that the cladding system is a repeating panel system. And so the curved surfaces are rationalized so that they can be clad, 80% of the surface of the building can be clad using just 4 panel types. And this kind of standardization, of course, makes the system more economic. So you can see if we compare the Sainsbury Center and Bilbao, we can see through these two buildings the wide range of technical and aesthetic possibilities of metal cladding. They do have some things in common. So both buildings use the same system for walls and roofs. Both rely on standardized mass production of the cladding system, that is, standard panel sizes. But there the similarity ends, and there are many differences between the two buildings. The cladding system for the Sainsbury Centre is composite metal panels, that is, aluminum bonded to rigid insulation. The cladding system for Bilbao is flat sheet titanium. The composite panels of the Sainsbury Centre are rigid and they span 6 feet uh, from subframe to subframe. The titanium panels of Bilbao are super thin and flexible and need a continuous substrate of galvanized metal sheet, galvanized steel sheet, to support them. On the Sainsbury Centre, the cladding panel provides a finish both on the exterior of the building and the interior. So we have a very thin sheet of aluminum bonded to both the outer and the inner face of the cladding panel. On Bilbao, the titanium cladding is an exterior finish only. Both buildings are silver, but the color of the silver on the Sainsbury Centre is a paint finish on the aluminum panels. The color of the cladding of Bilbao is the titanium itself. The jointing systems are different. So the joints on the Sainsbury Centre are the neoprene gaskets. And this, as you remember, we discussed this as being a very innovative system. The joints on Bilbao are flat seam uh, metal roof joints, in which the joint is made by interlocking or folding over layers of metal to join them together. This is a very traditional system, has been used for thousands of years, including on the Pantheon. And then the buildings have very different aesthetics. So the Sainsbury Centre is precise, crisp. It is machine made. It does not have a human imprint. And the aesthetic of Bilbao is soft and sensuous and handcrafted with a human imprint. Okay, that's it for today. Thank you very much.